The topic in 4.10 in our book deals with antiderivatives, which is kind of a fun topic and a very important topic. Because in much the same way that Calculus 1 is completely devoted to finding derivatives, it's a bit of an oversimplification as we've seen, kind of a lie here, but hopefully close enough. Calc 2 is completely devoted to finding antiderivatives. Again, that's not entirely true, but there's at least some semblance of truth in there. Antiderivatives are going to end up being really important to Calculus 2, and in 4.10 we get introduced to antiderivatives. So what is an antiderivative? Well, really all it is kind of the inverse, loosely speaking, of a derivative. The derivative of x cubed equals 3x squared. Therefore, an antiderivative of 3x squared would be x cubed. If you're paying really close attention, you might note that I said an antiderivative of 3x squared is equal to x cubed, because it turns out that 3x squared has more than one antiderivative. And that's because there's more than just this one function whose derivative is 3x squared. For example, the derivative of x cubed plus 1 would be equal to 3x squared, because when we're taking the derivative of a sum of terms, all we have to do is find the sum of their derivatives, and the derivative of any constant is just equal to 0. So because the derivative of x cubed plus 1 equals 3x squared, another antiderivative of 3x squared would be x cubed plus 1. That's already a little bit annoying that we have multiple answers to the same question, the question of what is the antiderivative of 3x squared. So typically what we do to get around that is we define the antiderivative of 3x squared to be x cubed plus c, where c represents any constant. And that's not specific to this antiderivative 3x squared. Anytime we take an antiderivative, we're going to tack on a plus c to our answer, because the derivative of any answer plus c is the same as the derivative of that answer, x cubed in this case. To see if that makes sense, I could ask you a question like, find the antiderivative of 1 divided by 2 times the square root of x. That's a really difficult question, and not one I'd expect you to be able to answer right now, but maybe you remember this being an answer to a question earlier on in the class. Maybe you remember somebody, me I guess, asking you to figure out the derivative of the square root of x. And maybe to do that, you say, well, the square root of x is the same as x to the 1/2 power. So if I use the power rule, I bring that 1/2 down in front, and then I subtract 1 from the exponent to get 1/2 x to the negative 1/2 power, which I can rewrite as 1 divided by 2 times the square root of x. Because the negative exponent puts this down on the bottom of the fraction, and the 1/2 means take the square root of it. If you happen to remember this fact that the derivative of the square root of x were equal to 1 divided by 2 times the square root of x, then it'd be easy enough to figure out the antiderivative of 1 divided by 2 times the square root of x. Because you'd be like, wait a minute, I recognize that thing. That was the answer to a question. What question? The question of what is the derivative of the square root of x. So if 1 divided by 2 times the square root of x is the answer to the question, what is the derivative of the square root of x, then the antiderivative of 1 divided by 2 times the square root of x would just be equal to the square root of x. If you got that far, I'd be really proud of you. I'd be like, that's great. But then I'd be like, but technically, the square root of x is not the only function that we could take the derivative of and get 1 divided by 2 times the square root of x as the answer. If I asked you to take the derivative of the square root of x plus 49, you'd get this exact same answer. So while the square root of x is an antiderivative of 1 divided by 2 times the square root of x, the antiderivative of 1 divided by 2 times the square root of x technically should be the square root of x plus c. What you'll see is this c is kind of annoying. You're often going to forget to write it as your answer, and it's not going to be a big deal. But I'm always going to put it in my answer. I'm going to try to remind you to tack on a plus c anytime you're finding antiderivatives. But I don't want to harp too much on the plus c part. What I want to talk about now is how would I, the student, have recognized that the antiderivative of 1 divided by 2 times the square root of x is equal to the square root of x, plus the c technically, if I didn't have this memorized? If I didn't recognize that this was the answer to this question, how would I ever figure out the answer to this question? If you're thinking along those lines, that's really good, because we don't want to rely upon answering antiderivative questions by recognizing derivative answers. That's very inefficient. What we want to do instead is develop some rules so that we can take the antiderivative of 1 divided by 2 times the square root of x without thinking about this method that we have in red. I mean, since we're so good at this method in red, we might want to use this to check our answer, but it'd be nice if we could get the answer in blue to the question in green without recognizing the process in red. And that's what we're going to do in this section. Before I teach you how to do that, get the answer in blue from the question in green without thinking about the method in red, we're going to need some notation so that we can write these questions a little bit better. There's at least 3 different ways you can ask and answer questions about the antiderivative. I'll go back to this example of the antiderivative of 3x squared being equal to x cubed plus c to illustrate the different ways you can ask and answer that question. The first way is to tell somebody that there's some function f out there, and the derivative of that function is 3x squared, so what you, the student, need to do is find f of x. This is probably the notation that makes the most sense to a student who's very familiar with Calculus 1. I could say f prime of x equals 3x squared. I could ask you to find f of x, and what you would say is f of x equals x cubed. Maybe you'd even say x cubed plus c if you were really impressive. And this would make sense as a question and an answer. But that's not the only way you can encapsulate this information. Another way you could do it is say that there's some function f of x that equals 3x squared. And you could ask somebody to find capital F of x. And what you need to know about that is that capital F of x means the antiderivative of the function f of x. Well, it's perfectly fine to tell the student that f prime of x equals 3x squared. That might seem a little bit weird. What if I just say there's some function out there, f of x equals 3x squared, and I want to know what is the antiderivative of that function? If I'm looking for the antiderivative of a function, it might seem more natural to state that function using our function notation, f of x equals 3x squared. But if I'm using f of x equals 3x squared as the question, how would I state the answer? Well, let's just invent some notation. Why don't we make capital F represent the antiderivative? And that's not just you and me inventing some notation, that's the standard notation that people mean. Saying that f prime of x equals 3x squared and asking somebody to find little f of x is the exact same as saying little f of x equals 3x squared and asking somebody to find capital F of x. In both cases, the answer is x cubed plus c. We're just using different notation to denote that answer. And the notation doesn't end there. And you're like, come on, man, that's enough notation. I think you're going to like this third piece of notation. Because if you think back to derivatives, when we first learned derivatives, the way we stated them is I said f of x equals x cubed, and then I said find f prime of x. And it was sort of two different mathematical sentences here. If I wanted to say that the derivative of x cubed equals 3x squared, I could write it like this with two different equations, but that's kind of inefficient. It would be nice if I could write this all in one sentence, all in one line as one equality. And it turns out that you can. We learned this d over dx symbol that did exactly that. I told you to think about it like d over dx means take the derivative of. So both of these equalities are captured in this single equality that says the derivative of x cubed equals 3x squared. If you take the derivative of this expression x cubed, you get as your answer 3x squared. It'd be nice if there was something kind of like that for antiderivatives, because right now we only have ways to state antiderivatives with two lines. This equality and this equality encapsulates the fact that the antiderivative of 3x squared is x cubed plus c. And this equality together also encapsulates that exact same information. But could we do it all in one line? Absolutely we can. We just need a new symbol. We need the antiderivative version of this d over dx symbol. And for reasons that will be apparent in a Calculus 2 class, the symbol that we use to mean take the antiderivative of is this weird little S-looking symbol. It's called an integral, or more specifically, an indefinite integral. And it's kind of a strange symbol because it's sort of broken in half. This little S thing, along with this dx thing, means take the antiderivative of. And I know that's a little weird, but if you think about it, this was kind of weird too, having this written as a fraction that kind of had these two different parts, d divided by dx. These symbols weren't chosen for no reason at all. This kind of weird S-looking symbol and this dx right here each have meaning, kind of related, loosely speaking, to this symbol up here, but we're not worrying about any of that now. That's all problems for a Calc 2 class. For now, I just want you to recognize when you see these symbols, they'll come together, and whatever is inside of those two symbols, 3x squared, is the thing you need to take the antiderivative of. So when I write this little symbol with a dx there, and then choose a function like, I don't know, 3x squared to put in between them, the way you read that is, oh, you want me to figure out the antiderivative of 3x squared. No problem, that's x cubed, or technically x cubed plus c, because the derivative of x cubed plus c is 3x squared. All three of these notations are perfectly fine, and what you'll see is each of the three has their advantages and their disadvantages. The bottom one might end up being the most useful to us, but you really should be comfortable with all three. As I mentioned earlier, I want to be able to ask you this question. Maybe I could write this integral symbol, 1 over 2 times the square root of x dx, and you'd be like, oh, you want me to take the antiderivative of 1 over 2 times the square root of x. And I'd want you to be able to answer that question without just recognizing that 1 divided by 2 times the square root of x was the answer to a derivative question. I want you to have a series of steps that you can do to figure out that this antiderivative is equal to the square root of x plus c. And those series of steps that I'm referring to will be very similar to a series of steps that we used to take derivatives. Just like we had a bunch of derivative rules that we had to apply to given expressions so we could take derivatives, we're going to have a bunch of antiderivative rules that we apply to given expressions so that we can figure out antiderivatives. And what's kind of nice is those rules are going to be really closely related. I know it might feel a little bit overwhelming because we have so many derivative rules. This is an incomplete list of the rules for differentiation, in other words, taking derivatives, that you see in a Calculus 1 class. We have these different building blocks, the power rule, exponent, logarithmic, trig, inverse trig results, and then we also have these rules on how you put stuff together, right? Coefficients you can kind of ignore, sums and differences if you're taking derivatives, just take the derivative of the terms individually, the product rule, the quotient rule, the chain rule. I mean, we spend months learning all these different rules. What we're kind of going to need are different versions of each of these different rules that sort of work in reverse. Because we're not interested in taking derivatives, we're interested in taking antiderivatives. I'm definitely not going to go over all those in this video, but I do want to talk about 2 of the rules that will be really useful to you. The first that I want to talk about is this coefficient rule. You probably don't even think about it much at this point, but it's really important that if you're taking the derivative of, 10x to the 5th power, that you can completely ignore that 10 and just take the derivative of the x to the 5th power. As you know, the derivative of x to the 5th power is 5x to the 4th power. Therefore, the derivative of 10x to the 5th power is just 10 times 5x to the 4th power. In other words, 50x to the 4th power. Well, if we can ignore coefficients when we're taking derivatives, it kind of makes sense that we should be able to ignore coefficients when we're taking antiderivatives. Right? If the derivative of 10x to the 5th is 10 times the derivative of x to the 5th, then the antiderivative of 10 times 5x to the 4th will just be 10 times the antiderivative of 5x to the 4th. Just like we have the coefficient rule for derivatives, we have a coefficient rule for antiderivatives. And it works in almost the same way. If we're being asked to take the antiderivative of, so there's my antiderivative symbol, some constant times a function. So a f of x dx, where a represents a constant and f of x represents a function. What we do is we take that coefficient and pull it out in front of the antiderivative sign, and then just take the antiderivative of the function, f of x dx. Rather than write it this way, the way I'm going to write this is a times capital F of x. The antiderivative of a f of x dx is equal to a times capital F of x. And you might be like, wait a minute, shouldn't you tack on a plus c? Well, I actually don't have to here because the capital F of x contains the plus c, right? Remember, capital F of x is the antiderivative of lowercase f of x. So capital F of x already has the plus c as part of it. So I don't need an extra plus c. Earlier, we talked about the antiderivative of 3x squared being equal to x cubed. But if we're instead being asked for the antiderivative of, 300x squared, one way we could do this problem is by recognizing that 300 is 100 times 3. So this is really just the antiderivative of 100 times 3x squared dx. And if we treat this 100 as a coefficient, we could say it's 100 times the antiderivative of 3x squared. We already know that the antiderivative of 3x squared is x cubed. So our answer would be 100 times x cubed. And if you can remember, tack on a plus c. A couple minor things here. The first one is, earlier we said that the antiderivative of 3x squared dx is equal to x cubed plus c. Over here I have 100 times the stuff in red. But the stuff in red contains 2 different terms, the x cubed and the plus c. So if I have 100 times x cubed plus c, shouldn't I end up with 100x cubed plus 100c? I doubt you were thinking that, but if you are, that's really impressive. Technically, this could be 100c. But the nice thing about 100 times some constant c is it's just some constant. C represents any constant. Any number we want could be right here. Remember, what this is supposed to encapsulate is if we took the derivative of this, no matter what number was taking the place of the c, we would get 300x squared for our answer. We don't need to change this to 100c because because 100c is just some other constant. Don't think too deeply about the c's. Do all the work that you're doing, and then when you're completely done with your work, just add on a plus c at the end. That plus c is really flexible. It represents any constant you want, so you don't have to worry about it changing, becoming negative, becoming a multiple, anything like that. The second comment that I want to make is, the coefficient right here was 300. And what I did in this problem is, I broke that 300 up into 100 times 3, and then only used the coefficient rule on the 100. Why didn't I bring the 300 out in front of this antiderivative symbol? Right? Couldn't I have taken this problem right here and said the 300 is just a coefficient, so let's pull that out in front of the integral symbol and figure out the antiderivative of x squared dx? And the short answer is absolutely. In fact, we're going to end up doing the problem this way. But the reason I didn't do it this way is because I wasn't confident that you'd be able to recognize the antiderivative of x squared. I knew you'd be able to figure out the antiderivative of 3x squared because we talked about that up here. That's the example we've been doing throughout this video. The antiderivative of 3x squared is x cubed. But what's the antiderivative of x squared? Is this something you're able to figure out? I'm sure if you thought deeply enough about it, you could have, but it's not obvious what the antiderivative of x squared is. To figure out the antiderivative of x squared, we really need to think about our power rule kind of in reverse. And that's the other antiderivative rule that I want to talk about in this video. The reason the derivative of x cubed is equal to 3x squared is because when we use the power rule and we take the derivative of x to the n power for any number n, we get n times x to the n minus 1 power. But what would the power rule for antiderivatives look like? Well, first of all, we wouldn't be taking the derivative of something, we'd be taking the antiderivative of something. So there's my antiderivative symbol. What are we taking the antiderivative of? Well, we want x raised up to some power. I want to keep this really general, so I don't want to write x to the third power. I instead want to write x to the n power. And what I'm supposed to do is figure out what goes over here on the other side of the equation. Well, it'll be something plus c. I'll tack on that plus c right now so I don't forget. But what will that something be? Well, whatever I write in this orange box right here, when I take the derivative of what's in that orange box, I better end up with x to the n power. So if you think about taking the derivative of what's inside this box, if the expression is going to kind of look like this expression, it'll be x raised up to some power, but that power will not be the n power. You're like, right, it'll be the n minus 1 power. No, because if we're taking the derivative, we subtract 1 from the exponent. So when we're taking the antiderivative, we'll have to add 1 to the exponent. Because if we want the antiderivative of x to the n power, we have to think about what could we take the derivative of to make x to the n our answer. If we want x to the n to be our answer, we're going to be using the power rule, and the power rule tells us to subtract 1 from the exponent. So if we start out with x to the n plus 1 and then use the power rule, we subtract 1 from the exponent and end up with x to the n. And you're like, no. You're forgetting the part about taking that exponent and bringing it down in front, right? The power rule doesn't just subtract 1 from the exponent. It also takes the exponent and brings it down in front. So this can't possibly be the right answer. N plus 1 minus 1 would yield the x to the n that I want, but I'd have this extra coefficient, this n plus 1 coefficient that I don't want. How can I get rid of that n plus 1 coefficient? What if I just divide by n plus 1? The power rule for antiderivatives states that the antiderivative of x to the n power is 1 divided by n plus 1 times x raised up to the n plus 1 power. If that feels a little bit weird, try plugging in some values. Maybe let's test this with n equal to 3. If I change all the n's into 3's, what I'm saying is the antiderivative of x cubed is equal to 1 divided by 3 plus 1, in other words, 1 divided by 4, times x raised up to the 3 plus 1 power. 3 plus 1 is 4, it'd be x to the 4th power. Don't forget to tack on your plus c. Is that right? Is the antiderivative of x cubed equal to 1/4 x to the 4th plus c? Well, let's check it. If the antiderivative of x cubed equals 1/4 x to the 4th plus c, then the derivative of 1/4 x to the 4th plus c better be equal to x cubed. Is it? Well, if we're taking the derivative of something plus something, we take the derivative of each term individually. So we take the derivative of 1/4 x to the 4th and then add to that the derivative of a constant. This 1/4 is a coefficient. I can pull that out in front of my derivative symbol. So the derivative of this expression is the sum of these two terms. We already know that the derivative of any constant is just equal to 0. Over here, the 1/4 is out in front of this d over dx symbol, so we don't need to do any calculus there. We just have to take the derivative of x to the 4th power. The derivative of x to the 4th power is 4x cubed, so we get 1/4 times 4x cubed plus 0. 1/4 times 4 is just 1, so we get x cubed plus 0. In other words, x cubed. Is that right? Yeah, that's right. The derivative of the right side of this expression equals the thing we're taking the antiderivative of. Therefore, the antiderivative of this thing must be the right side of this expression. If this feels a little bit confusing, it should. It really hurts your head to kind of go back and forth between derivatives and antiderivatives. You really have to be an expert with derivatives to even begin understanding antiderivatives. But once you start to get the hang of it, it's kind of fun. They're tricky little puzzles that you have the ability to solve. Before I end this video, let me take you back down here to this example, the antiderivative of 300x squared, and let's solve that in a way that'll end up being more efficient. Rather than recognize that 300 is 100 times 3, and we know the antiderivative of 3x squared, let's take the entire coefficient 300 and bring that out in front of our integral symbol. Instead of the antiderivative of 300x squared dx, we got 300 times the antiderivative of x squared dx. What's that going to be equal to? Well, the 300 is out in front of the integral symbol, so there's nothing for me to do there. All I have to do is take the antiderivative of x squared. What's the antiderivative of x squared? Think power rule, but playing the role of the n is a 2. I need some expression so that when I take the derivative of that expression, I end up with x squared. What would that expression be? Well, it would have to be x cubed, right? Because I'm going to subtract 1 from the exponent. And if I want a number that I subtract 1 from to end up with a 2, that number must be a 3. But it's not just x cubed, because if you were taking the derivative of x cubed, you would not get x squared. You'd get 3x squared. You have that extra 3. So what we have to do is multiply by 1/3. Technically, we should tack on a plus c, and maybe you should argue there should be parentheses right here, but we don't have to worry about those parentheses because 300 times some constant is just some constant. So we can leave those parentheses out and just simplify this expression to be done. 300 times 1/3 is 100. We get 100x cubed plus c for our answer. If you're not feeling good about 100x cubed plus c for your answer, we can always check these. Take the derivative of 100x cubed plus c. You're really good with derivatives at this point. You could probably take the derivative of this without writing a single thing down. You could just look at it. Be like, I got 2 terms. The derivative of the second term is just 0. So really, I'm just asking myself the question, what's the derivative of the first term? That 100, don't worry about that. I'll multiply by 100 at the end. I just got to take the derivative of x cubed. Derivative of x cubed, that's something I learned months ago. I'm using the power rule that derivative is 3x squared. So I got 3x squared times the 100. I got 300x squared. Oh, nice. That's exactly what I was asked to take the antiderivative of. The derivative of my answer is what I was asked to take the antiderivative of. Therefore, the antiderivative of this thing is my answer. Good news and bad news. The bad news is there were a lot of derivative rules, right? We've only talked about the power rule and this coefficient rule, but look at all these other rules that we have down here. We just spent like 20 minutes talking about those rules. What about the rest of these? It's not as bad as it seems. If you can wrap your head around these 2 rules kind of in reverse and understand this process, if you're able to figure out that the antiderivative of 300x squared dx is equal to 100x cubed plus c, you'll be able to do everything else we need in this section. We're going to tack on some more rules, but they won't be any more complicated than what we just did. But what we just did is pretty hard, so this feels like you might need a breather, so I'm going to end this video here.